Hey everyone, welcome back to linear algebra. This will be lecture 2 of the course. And in this section, we're going to get into something called the dot product. Now, if you took Calculus 3, you will have had some experience with the dot product. It comes up early in that course as part of the gear up for three-dimensional calculus. But here we're going to give it a little more thorough of a treatment. We're going to delve into it a little bit deeper. And so this is just the first of several different types of products that can be defined on vectors. So we'll get started on this. Let's jump into this. We'll call it section 1.2, the dot product. Okay, let's go ahead and define the dot product. We'll start with the definition, and then we'll build up some properties, do some examples, etc. So let x be a vector, and we'll go ahead and write out some of the components here, x1, x2, up to xn. And we'll let y be another vector. We'll call y1, y2, yn. Okay. So these are two vectors, so x and y. We'll let them be two vectors in Rn. Okay. The dot product, or sometimes called the inner product, okay, the dot product or the inner product of x and y is given by the following. So x dot y, that's the notation we'll use, and basically it's going to be what you think of as a sum product of the components. So it's x x1 y1, right, multiplied together, plus x2 y2 multiplied together, plus dot 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 xn yn multiplied together, right? I suppose you could succinctly denote it using summation notation as I equals 1 to n of xi yi. Okay, so basically we just want to take all of the components and add or multiply them against their corresponding components, and then add all of those products up, and that is what we call the dot product or the inner product. Okay, very good. Let's do a simple example and make sure we have this idea. So let's let x equal 2, -4, 3, and y equal 1, 5, -2. Then x dot y is 2 times 1, plus -4 times 5, plus 3 times -2, right? So 2 times 1, -4 times 5, and 3 times 2. Okay, and so what do we get here? Well, what do we have? 2 minus 20 minus 6, so -24. Okay, so the dot product yields a scalar. Okay. Okay. All right, so that's the idea of the dot product. Now we're going to use this, well, forever. For the rest of the course, it'll come up almost probably in every single lecture. It's one of the fundamental things one of the fundamental tools that we have in linear algebra. Let's talk about some of the properties of the dot product. So let's talk through some of the properties here. So let's let x, y, z be vectors in Rn. Okay, and c is a scalar. Okay, so then what do we got? Well, the dot product is commutative, so x dot y is the same as y dot x. Okay, so the dot product commutes. Okay. If you dot a vector against itself, then that is the same as squaring the norm of the vector. Okay. All right, so a vector dotted against itself gives you the same output as squaring the norm of the vector, right? And it's always greater than or equal to 0. Okay. All right. And we'll come back through and prove a couple of these, but let's keep moving. Some of these are very straightforward to prove, but let's take a look at another one. X dotted against itself equals 0 if and only if the vector x is the 0 vector. Okay. Right, so the number 2 says that dotting a vector against itself is equal to the square of the norm of the vector, and it's always greater than or equal to 0. Number 3 says it's equal to 0 if and only if x happens to be the 0 vector. All right. A constant, right? So you get your scalar here, and then x dot y. What can we do with this? Well, associativity works here. So you can multiply the scalar times the vector first, and then dot that resultant vector against the vector y. Or you can even do this. You can take x and then dot that against cy, right? So you can multiply the scalar by either of the two vectors in the dot product and then dot against the remaining vector and get the same result. So it's a kind of like a form of associativity. Okay. Very good. How about this guy? So x dot y plus z. All right, so I've got y plus z is going to give me a vector, and an x dotted against that vector is going to give me a scalar. Now it turns out you can use something like the distributive property here, right? So I can go x dot y plus x dot z. And so it works like the familiar distributive property that we're all used to. And then finally the result, the kind of the reverse is true as well. So you can dot on either side, right? Because the dot product is commutative, this would make sense that you could do something like this. X plus y dotted with z is also going to work the same way. So you'd have x dot z plus y dot z. Okay. So many of these can be proven by merely kind of expanding the expressions on both sides and showing they're equal to one another, right? So this is great practice, right? If you're learning proofs, linear algebra is usually one of the first courses you'll take in college, where proofs are kind of the point of the course, right? So you get a theorem, you're you're shown the proof, asked to prove it. Proofs are really like the point of mathematics in some sense. So these are all great examples to practice on. Linear algebra proofs tend to be, at least in the elementary linear algebra world, tend to be fairly easy to comprehend, and more often than not, they're just kind of direct proofs as well, which is nice, specifically when you're learning about how to prove things. But let's prove a couple of these. I'll not prove all of them, but let's prove the first one, right? The first item, and that's namely that x dot y is equal to y dot x. Okay, x dot y is equal to y dot x. And so this one is really straightforward to do. We can just start with x dot y. Right? We know what x and y are. That's x1 x2 dot 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 xn dot y1 y2 dot 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 yn, right? When I dot these together, then I take the corresponding components, multiply them together, and then add all of the products. And so this would be x1 y1 plus x2 y2 plus dot 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 plus xn yn. Okay, now I guess technically, let's not put it in front. This is not a vector anymore. This becomes a scalar, right? A real number. Now notice that in this expansion here, x1, y1, these are just real numbers, right? So x1 and y1, you could easily reverse the order of them, right? So in particular, I could write y1 x1 plus y2 x2 plus dot 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 plus yn xn, right? I mean, because these are just real numbers. I mean, this is like 2 times 4, same as 4 times 2. I can reverse the order, right? And so when I do that, then I can pull them apart again in just the same way as I did up here, right? So this is going to be equal to the vector y1 y2 dot 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 yn dotted against x1 x2 dot 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 xn, right? Which is of course y dot x. Okay, so x dot y equals y dot x. So the dot product is a commutative operation. Okay. All right. So that proves one. Now the others are most of them are very much like this. You know, a lot of times in linear algebra, and I think I might have said this last time, but a lot of times when you're proving things, it's a good idea just to take the vector, break it apart into its more like component-y version of itself, do the operation, expand it, and rearrange when you can, and then kind of sometimes frequently just reverse the operation. Right. So I think for that reason, linear algebra proofs are somewhat more, they're somewhat easier to understand. And I think that's a lot of the reason why we kind of start with linear algebra as the course to learn proofs in. So they're not always easy, that's for sure. That's definitely for sure. But at least at at the elementary linear algebra level, they tend to be a little more straightforward. Okay. All right, so let's take a look at another theorem that relates to the dot product. And this theorem is called the Cauchy-Schwarz inequality. Okay, so this is the Cauchy-Schwarz inequality. Okay, kind of a famous one, used a lot. And so what the Cauchy-Schwarz inequality gives us is it provides us with a upper and lower bound on the value of the dot product. Okay, so what does it say? It says if x and y are vectors in Rn, then the absolute value of the dot product of x and y is less than or equal to the product of the norms of the two vectors, right? So careful with the notation here. So over here you got single bars. We're talking about an absolute value here, right? So x dot y is going to give you a real number. Could be positive, could be negative. This is the absolute value of that, right? And then over here, you're talking about, this is the norm of x, right? So this is x1 squared plus x2 squared plus dot 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 plus xn squared. Take the square root of it. That's the norm of x. Same thing for y. Identify the two norms, multiply them together, and the Cauchy-Schwarz inequality says that in all cases, the absolute value of the dot product is less than or equal to the product of the norms. Okay, so this one, let's prove this. Okay, so we'll take a couple cases. Case one, Case 1, if case 1 is going to be the case where one or the other or both of the vectors are the zero vectors. So if x equals a zero vector or y equals a zero vector. Okay. So if that's the case, then, right, so if the dot product in this case is equal to 0, right? Right, if one of the vectors has all 0 components, when I multiply it against the other one, all of the products will be 0, right? So you just have 0 plus 0 plus 0, etc. And so in that case, that's going to be less than or equal to right. So if x is the 0 vector, then the length of x is 0, so this will be 0. If y is a 0 vector, this will be 0. Either way, one or both of these are 0, and so this has to be equal to 0. Okay, so case 1 is sort of the trivial case where one of the two vectors, where at least one of the two vectors is 0. Okay, so that one holds up. Okay, so that's case 1. Case 2 then, okay, assume x and y are not the 0 vector. Okay, so neither of them are the 0 vector. Then what happens? Well, what are we trying to show here? So we wish to show, what do we wish to show? We wish to show that that the absolute value of x dot y is less than or equal to the product of the norms of the two vectors. Another way to say that is to say that x dot y is between these two, right? It's between this. Okay, oops, I'm writing this really sloppy. Okay. Right, so we can kind of unpack this thing here. Oh, and sorry, this should say negative. There we go. And so this is going to be true, right? This is true, right? This implies that negative 1 be less than or equal to x dot y over, okay, I'm going to write it like that. I'm going to ditch the parentheses going forward. Right, I can divide both sides by the product of the norms here. Okay. Okay, so this is true if and only if that is true. Okay, and so let's move on here. Hold on one second, let me switch my page here. Okay, so negative 1 is less than or equal to x dot y, which is less than or equal to 1. Okay, so note, right, so notice that x dot y over this product of the norms of the two vectors is equal to x over the norm of x dotted against y over the norm of y. Now that comes from so this comes from sort of some properties that we discussed previously of constants and how the dot product and constants can interact, right? So this hopefully this is clear, but you can kind of break each of these pieces up, think of them as 1 over the norm of x, 1 over the norm of y as a constant, and so they can be broken apart in the dot product here. Okay, and we're going to just call these a dot b. Okay, vectors a dot b. Now, the key here is both a and b as defined are unit vectors. Okay, so these are both unit vectors. Okay, and so what we really need to show is that we really need to show that -1 is less than or equal to a dot b, which is less than or equal to 1. Okay. A dot b so here's where we're going to get a little tricky, right? This is a little bit of a tricky proof, actually. So what we're gonna do is we're gonna kind of expand a dot b in a kind of a strange way and show that this all works out, right? So a dot b occurs as part of the expansion of a plus b dot a plus b, right? So a dot b occurs as part of the expansion, right? Expansion of a plus b, right? Remember, these are just vectors dotted with a plus b. Okay, as well as a minus b dot a minus b. Okay, so let's start with this one and see what happens here. So if I take a plus b, a vector, two vectors added together gets me another vector, dot a plus b, what do I get? Well, I know that that's equal to a plus b squared, right? So the norm of a plus b squared, right? Okay, and I know that it's greater than or equal to 0. Okay, and so then what? Well, a dot a, again, these are vectors, plus b dot a, just doing the expansion here, expanding this, plus a dot b, right, kind of foiling these out, plus b dot b is therefore greater than or equal to 0. Okay, this guy here is just the norm of a squared, and then I've got b dot a and a dot b, so that I've basically got 2 times a dot b. And then this over here is the norm of b squared, so that's got to be greater than or equal to 0. And so a, remember, is a unit vector, and so is b. They're both unit vectors, so this and this are both equal to 1, so I have 1 plus 2 a dot b plus 1 is greater than or equal to 0. And so obviously that means I've got 2 plus 2 a dot b is greater than or equal to 0, implying that, let's see, twice a dot b is greater than or equal to -2, right? And so I can now, at this point, I can divide by +2. And so that means a dot b must be greater than or equal to -1. Okay? And so what this shows is that if a and b are 2 unit vectors, then their dot product is greater than or equal to -1. Okay? And so this shows, this gets us half of the inequality. All right? And then what you can do is you can run the exact same argument using this one here to get the other half of the inequality. Okay, so you'd run the exact same argument. You would say, all right, a minus b dot a minus b equals the norm of a minus b squared, which is greater than or equal to 0. And then you expand it just the same, except it's a minus b instead of a plus b. Right? And then you consolidate and do your work, and then when you get down to the bottom here, you're going to end up having a negative right here, I believe. And when you do that, you divide by the positive, and you end up getting a dot b is greater than or equal to, or greater than or equal to, or less than or equal to 1, right? Because you'll divide by a negative, flip the inequality, right? So bottom line is it basically runs the exact same way, except it starts from this vantage point. Okay, and then once you have done both of those, you get this side and you get that side, and so that implies the result. And so it follows that -1 is less than or equal to a dot b, which is less than or equal to 1, which implies the result. Okay, so so obviously pause the video, take a moment to make sure that you can perform that exercise. But I think this is a good blueprint for how to do it, but you just have to you change the identity you start with to a minus b dot a minus b. Okay. All right. Very good. That's the proof for the Cauchy-Schwarz inequality. And from the Cauchy-Schwarz inequality, we get to another important inequality that will be used extensively, and that is the triangle inequality. Okay, so this is the triangle inequality. Okay, and this one, as we work through the proof of this one, you'll see that this one draws directly from the Cauchy-Schwarz inequality. One of the lines of the proof references it specifically and says that because of the Cauchy-Schwarz inequality, this is true. So this is instructive as well as you're sort of starting out your career proving things, that you realize that things that have come before once you've proven it once, you can use it successively, and that's kind of it's kind of how mathematics is built up from the ground up. It's one giant theorem lattice, really. Okay, so let's talk through the triangle inequality. So if x and y are vectors in Rn, okay, in Rn, then x plus y, the norm of x plus y is less than or equal to the norm of x plus the norm of y. Okay, so the norm of the sum of the vectors is less than or equal to the norm of x plus, separately, the norm of y. Okay, so this is called the triangle inequality because it's sort of very easy to see when you just kind of make a triangle here. So if I have a vector x, like that, looks like that, then I have another vector y, and I kind of arrange them in this fashion, right, tail to tail, then x plus y produces this vector, doesn't it? We've seen this, we saw this in the previous section. You get this third vector from the sum of these two. So all this is saying is that the length of the third vector, namely the length of this thing, has got to be less than or equal to the length of these two. Okay, so if the third vector x plus y is built up of the other two, x and y, then the length of x plus y needs to be less than or equal to the length of x plus the length of y. All right. And so it's very intuitive when you see it in a drawing like this. Okay. All right. Okay, so let's go ahead and prove this. Okay, and for this proof, we're going to start with this guy, x plus y squared. Okay, we're going to start with this, and then we'll get to the result itself. Notice the result is not x plus y squared, but we're going to start with this for our proof. Okay, so we can start to expand this, and we can see that this, we know from previous theorem that this is equal to x plus y dot x plus y, and we know that we can expand this, and this is equal to x dot x plus 2 times x dot y plus y dot y. Right, these are all vectors. Okay. And we know that x dot x is the same as the norm of x squared. And this is going to be 2 dot plus 2x dot y still. And then, of course, on the other side, y dot y is the same as the norm of y squared. Okay. Now, here's where we'll start to so this guy here is going to be less than or equal to. Now what we're going to do is so first thing we're going to do is we're going to convert this to an absolute value. Okay, so this will be 2 times the absolute value of x dot y. Right? So in that case, like if it was negative here, this would be less than this. Right? But if they're both positive, then they'll remain equal. Right? So all this is doing is potentially making this one larger. Okay, so that's not a problem. And then we're going to, by doing that, we've set up this middle term so that we can apply the Cauchy-Schwarz inequality. Okay, and so what we can say now is that the norm of x squared, so this guy here, the norm of x squared plus 2 times the absolute value of x dot y plus the norm of y squared is less than or equal to the norm of x squared plus 2 times, and then it's the norm of x times the norm of y. Right? These are, again, scalars, so they're just multiplied together normally, and then plus the norm of y squared. Right? So we've got an inequality here, right? So we had a strict equality up to this point, and then we said, oh, we're going to make this an absolute value here. And so that means this one could get bigger. If, in particular, if x dot y was negative here, it would now be positive, which makes the sum larger. Okay, so that's why we need the inequality. And then similarly here, we're going to use the Cauchy-Schwarz inequality to go from here to here. And we know that this could be bigger than this. Okay, so I'll just put a note here. This is the Cauchy-Schwarz inequality happening between these two lines. Okay. All right, but then once you get it to this section, right, we know that this is going to be equal to, what is it? Well, it's the norm of x plus the norm of y squared. Okay. Okay, so what have we shown? We've shown that the norm of x plus y squared, right, the norm of the vector x plus y, when you square that norm, that's going to be less than or equal to the norm of x plus the norm of y quantity squared. Okay, so this is less than or equal to this guy here. Right, and that's not what the theorem's about, but we can easily just take a square root of both sides, right? Right, so if I take the square root, then I get what I'm really after, which is this guy. Perfect, right? That's exactly what I want. So if I take the square root of the square over here and I take the square root of the square over here, then I get this. And so that's the triangle inequality. All right, excellent. Okay, so we've proven the triangle inequality as well as the Cauchy-Schwarz inequality. Great. Okay, so that's that part. Now, let's talk a little bit more about what the dot product can do for us. So the dot product, I mean, in addition, it's this number that gets spit out when we do a sum product on the components of two vectors. So you get some number, right? But additionally, the dot product enables us to find the angle between two vectors. Okay, so if I have, for example, some vector y and some other vector x, right, and I want to know the angle between them, the dot product can help me with this, right? So right now we're talking about xy vectors in R2 or R3 for now, because those are sort of the spatial realms that we're kind of used to, right? So that's what we're talking about right now. We'll later expand this to Rn in general, but let's start here, right? So let's say I have these two vectors drawn like this, and I've got a third vector then between the two, which I can just call x minus y. Okay. So the theta that we identify here, we're always, technically speaking, two vectors like this, x and y, they technically will identify two angles, right? So you got theta, the sort of smaller angle between them in this context, and then you got the larger angle outside. So we're always going to be talking about the angle that's between 0 and pi. Okay, it's always possible to do that, right? So we're always going to be considering theta to be the smaller of the two angles that are implied, and namely the angle that falls between 0 and pi. Okay, so given that, and given this triangle, if you can recall back to your trigonometry days, there was something called the law of cosines. Right, so it's called the law of cosines, right? And it's all about the relationship between the angles of a triangle and the length of the sides of the triangle. And so the law of cosines in our context would be stated like this: x minus y, the norm. Now remember, when I say norm, I'm just talking about the lengths. Okay, so the length of this side of this triangle that I've drawn out here is going to be equal to the norm of x squared plus the norm of y squared minus 2 times the norm of x times the norm of y times cosine of theta. Okay, and so this is, again, something called the law of cosines from trigonometry. If you went through a trig course, you definitely went through this, you talked through this, is a major topic there. There's also a law of sines as well. The law of cosines is the one that we're referencing here. And so just recall that in that trig class, it would have been, you know, A, B, and C, right? So maybe this is A, that's B, that's C, and then your angles were little a, little b, and little c, right? But this is a way to relate the sides of the length of the sides of the triangle to the angle of the angles of the triangle. And so there were different versions of the law of cosines. This is one of them. Okay, and so this is the law of cosines, just strictly speaking. But then we also have, right, something that we've just discussed. We know that the norm of x minus y, right, this length here, if we square it, we know that that's going to be equal to x minus y dot x minus y. Okay, which we know is x dot x minus 2 times x dot y plus y dot y. Okay, so that's just expanding this, right? So this is the identity we kind of discussed earlier in the lecture, but then this is just expanding that. And then also taking this thing here a little bit further, we know that this is the norm of x squared. And this over here is the norm of y squared. So in between I have this. Okay. Now, between these two equations, there's a couple of things that we want to first draw attention to this here, which I'm going to call 1. Okay, and then secondarily, I want to draw attention to this here, which I'm going to call 2. Now these two must be equal. Can we see why these two must be equal? Well, this expression here is equal to this. This expression here is equal to this, right? So that means this guy here and this guy here are equal. Probably don't need to write this out, but I'm going to just to make sure this is clear. Okay, so this is just 1. Well, sorry. Scratch that. This is the whole expression here. That's going to be equal to this. Okay, so I've got this and this, and I've got that and that, and so here's your 1, here's your 2, they're equal, right? Okay, so this is going to imply that -2 times the norm of x times the norm of y times cos theta is equal to -2 x dot y. Okay, x and y are all vectors here. Okay, and so then we can quickly just do a little bit of division, and we see that cosine of theta is equal to x dot y divided by this, the norm of x, the norm of y, times cosine of theta. Okay, and so x and y are 2 vectors in the plane. They share the same initial point, but obviously they share different terminal points. Theta is the angle between them. Okay, and so this formula will allow us to find theta, find the angle between them. Okay, let's do an example. Let's see how we can use this. Okay, so let's let x equal 6 comma -4 and y equal -2, 3. Let's find theta between x and y. Let's find the angle. So what we saw before was that the cosine of theta is x dot y over the norm of x times the norm of y. Okay, and so in this case, x dot y is going to be, well, let's write it out. So it'll be 6 times -2 plus -4 times 3. The norm of x is going to be 36 plus 16, so that is 52. The norm of y is going to be 4 plus 9, and so that is square root of 13. Okay, and so what do I get here? I get -24, so that's 12 plus 12, or sorry, -12 minus 12. So I get -24 over the square root of, so 52 is actually 13 times 4. Right, so I can kind of break this apart, and I get -24 over 2 times 13, and so I get -12 over 13. Okay, well, so that's what cosine of theta is equal to. I think I might have put a box around it a little too early. That's not exactly what we're after. Cosine of theta is equal to -12 over 13, and so we can just use the inverse cosine, like so, and plug that into a calculator, and you're going to get you'll get some value for that, right? Some angle in radians or degrees, depending on how your calculator set. Okay, but you can identify the angle between your x and your y just like that. Okay, so we kind of, I mean, intuitively, this sort of makes a lot of sense in R2 for sure, and even in R3 it makes sense. But in higher dimensional spaces, we sort of step outside of our everyday experience a little bit, right? And in such, in these kinds of things, like we haven't really defined what we mean by the angle between two vectors. But notice that what about higher dimensions? Well, notice that x dot y over the norm of x times the norm of y. So this ratio is always between -1 and 1. Right, we can see that because of the Cauchy-Schwarz inequality, right? So if this is true, then that means we can use this guy here. We can always run the inverse cosine on this. Means basically that whatever we get for this value here, it's going to be in the domain of the inverse cosine function, right? Which means we can do this for pretty much any vector in Rn. Okay, so we can do this for any vectors in Rn. Okay, and so that leads us kind of to this nice definition of what we mean by the angle between two vectors. It's intuitive what we mean by that in R2 and even in R3, but what do we mean by the angle between two vectors in 10-dimensional space in R10? Well, here's what we mean by it. Okay, so let x and y be two non-zero vectors in Rn. Okay, and then specifically n greater than or equal to 2, we'll say. Then the angle between x and y is the unique unique angle between 0 and pi radians, of course, whose cosine is equal to, and here it is, x dot y divided by the norm of x times the norm of y. Okay, so basically what we're saying here is that you can just extend this intuition into higher dimensional spaces. All right, so for n greater than or equal to 2, we can just use this definition, and it means the same thing as we go up into higher dimensions beyond R2 and R3. Okay, so it continues to work is the takeaway, the nice feature here. Let's do an example. Okay, let's let x equal -1, 4, 2, 0, -3, and y equal 2, 1, -4, -1, 0. What's the angle between these two vectors? Well, we just have to find the norm of x, right? And that's going to be -1 squared plus 4 squared plus 2 squared plus 0 squared plus -3 squared. Take the square root of that. The norm of y is going to be 2 squared plus 1 squared plus -4 squared plus -1 squared plus 0 squared. Okay, here you're going to get the square root of 30. Here you get the square root of 22. What's x dot y? Well, it's -1 times 2 plus 4 times 1 plus 2 times -4 plus 0 times 1 plus negative 3 times 0. Right? If you go through all of that, you get negative 2 plus 4 minus 8 plus 0, and so you get negative 6. Right? And so then the angle cosine of theta is equal to x dot y over the norm of x times the norm of y, which is negative 6 over the square root of 30 times the square root of 22. Okay, and so that means that theta, the angle between the two, is just going to be the inverse cosine of this number. Right, which you can plug in and check. Okay, I think you get about 103 degrees. Okay. All right. Excellent. Okay. I think we'll, well, one more theorem and then we'll take a pause before we jump into the next section. This theorem follows immediately from what we just discussed, from this construction we just worked through. So let's let x and y be non-zero vectors in Rn, and let theta be the angle between them. Then, a couple of things, right? First one, x dot y is greater than 0 if and only if 0 is less than or equal to theta is less than or equal to pi over 2. Second thing, x dot y is equal to 0 if and only if theta is pi over 2. And the third thing, x dot y is less than 0 if and only if pi over 2 is less than theta, which is less than or equal to pi. And this should be strictly less than, sorry. Okay. And so what is this saying? Well, it's saying the dot product is, starting with the middle thing in particular, the dot product is equal to 0 if and only if theta, the angle between the two vectors x and y, is pi over 2. Okay? And it's saying that the dot product is positive if theta is an acute angle, and the dot product is negative if theta is an obtuse angle. Right? Now if we kind of look up here, we can see that cosine of theta is equal to this, right? So we won't go through the proof formally, but I'll give you a sketch of what you want to check here. So the denominator here is always positive, right? So if this is going to be negative, if cosine of theta is negative, which it can be negative, obviously, then it's got to come from the dot product, right? And so the dot product is positive whenever theta is in the quadrant 1, right? So remember from trigonometry, imagine your unit circle. So over here, cos is positive. Over here, negative cos. Okay, and that's what this is saying. So if you're over here, then obviously your angle is between 0 and pi over 2, which means that this is a positive value. Well, this is always positive, so that means this must be positive as well. If you're over here, then that means your angle is between pi over 2 and pi, and that means cosine is negative, which means this is negative. Well, this is always positive, so if this is negative, then this has to be negative, and that's what you're seeing down here. Right, and then obviously right in the middle, cosine is 0 only in one place, and that's when theta is pi over 2. Right, and so this theta equals pi over 2 leads naturally into the next topic, which will be orthogonality. And we'll get into that in part B. So I'll end the video here, but we'll start up again with part B, and we'll wrap up with this dot product lecture. See you in a few.